The aim of this lecture is to help students learn how to come up with shear and moment equations for beams subjected to various loads. Representing shear and moment algebraically is very useful, as it allows the structural engineer to quickly identify critical stress areas in the beam. In most cases, it may not be possible to write down only one equation for shear or moment for the entire beam. Rather, it would be necessary to write multiple equations, one for each beam segment. This happens when the beam is subjected to one or more concentrated loads. For example, here there is a concentrated load at B. Since the load divides the beam into two segments, we need to write two equations for shear and two equations for moment, a pair of equations for each segment. Here, three pairs of equations are needed for representing shear and moment, since the concentrated loads divide the beam into three segments. The need for having multiple shear and moment equations also arises when the beam is partially subjected to distributed loads. For example, here, the uniformly distributed load divides the beam into two segments. Segment AB, which is directly under load, and segment BC, which is load-free. Therefore, we need one set of shear and moment equations for the left segment of the beam and another set of equations for the right segment of the beam. In this example, the triangular load divides the beam into three segments, AB, BC and CD. Therefore, we need three pairs of shear and moment equations, a pair for each segment. Now that we know it may be necessary to have multiple equations for representing shear and moment in beams, let's talk about how we should go about actually formulating such equations. Given a beam, we always start by calculating its support reactions. So step 1 is to calculate the support reactions. Step 2 is to decide how many shear and moment equations we need. That is, how many segments the beam is divided into by the loads. Let's spend a few minutes examining several cases here. How many pairs of shear and moment equations do we need for this beam? The load divides the beam into two segments. Therefore, we need two sets of equations. One set of equations for the left segment, another set of equations for the right segment. Here, the load does not divide the beam into multiple segments, as it is applied at the tip of the beam. Therefore, we only need one shear equation and one moment equation for the entire beam. Here, the loads divide the beam into three segments. Therefore, three pairs of shear and moment equations are needed. From these examples, it may appear that the required number of shear equations is always equal to the required number of moment equations, but this is not necessarily true. We could have loading patterns that make the required number of moment equations more than that of shear equations. Consider this beam. Here the beam is subjected to a concentrated moment at its midpoint. This causes a sudden drop, a discontinuity, in the beam's internal bending moment at the point. Consequently, two equations are needed for representing moment in the beam. We need one equation for the left segment up to the point of discontinuity. We need another equation for representing moment past the point of discontinuity. However, the concentrated moment does not cause any abrupt change in shear. Therefore, we can represent shear in the beam using one equation only. So, let's summarize what we have so far. To write shear and moment equations, first we calculate the beam's support reactions. Second, we determine the segments that the beam needs to be divided into for the purpose of formulating shear and moment equations. Now let's talk about the third step. In this step, we are going to cut the beam in each of the identified segments at some distance, say x, from the left end of the beam. For example, if this is our beam, we are going to cut it twice, once in segment AB and once in segment BC. Note that the distance from the left end of the beam to the cut point is labelled X in both cases. Then we draw the free body diagram for each segment. The fourth step is to formulate the equilibrium equations for each segment and solve them for the unknowns. Here, the unknowns are the shear and moment at the cut point. Let's go through this process using a simple example. Consider the simply supported beam subjected to a concentrated load of 10 kilonewtons. The load is applied 4 meters away from the left end of the beam. We wish to formulate the shear and moment equations for the beam. Step 1. Find the support reactions. This involves drawing the beam's free body diagram, formulating the equilibrium equations for the entire beam, then solving them for the unknowns. Step 2. Determine the required number of shear and moment equations. Here, the load divides the beam into 2 segments. Therefore, we need 2 sets of equations. We need a shear and moment equation for the left segment of the beam and another set of equations for the right segment of the beam. Step 3. Cut the beam in each segment. Then, draw the free body diagram of the left part of the beam. Here is the free body diagram when the beam is cut in segment AB. Here is the free body diagram when the beam is cut in segment BC. Step 4. Now formulate the equilibrium equations for each free body diagram. Then solve them for the unknown shear and moment. For the first free body diagram we get sum of the forces in the y direction equals 6 minus v equals 0. Sum of the moments about point O, the cut point, equals 6x minus m equals 0. Solving the first equation for v, we get v equals 6. Solving the second equation for m, we get m equals 6x. Since these equations are written for segment AB, they are valid only for x between 0 and 4. For the second free body diagram we have sum of the forces in the y direction equals 6 minus 10 minus v equals 0. Sum of the moments about the cut point, point O, equals 6 times x minus 10 times x minus 4 minus m equals 0. The first equilibrium equation gives us v equals negative 4. The second equation gives us m equals 40 minus 4x. This pair of equations work only for x between 4 and 10, where segment BC is located. Let's summarize the results. Shear in the beam is expressed algebraically using 2 equations. The first equation gives us the shear value in the beam when x is between 0 and 4. The second equation gives us the shear value when x is between 4 and 10. Similarly, moment in the beam is expressed algebraically using 2 equations. The first equation gives us the moment value in the beam when x is between 0 and 4. The second equation gives us the moment value when x is between 4 and 10. Moment at x equals 4 can be calculated using either of the moment equations. Before we end this session, let's examine another case. Here, half of the beam is subjected to a distributed load. The other half is not subjected to any loads. we wish to write shear and moment equations for the beam. Step 1. Find the support reactions. Step 2. Determine the required number of shear and moment equations. Just like the previous example, here the load divides the beam into two segments, AB and BC. Therefore, we need two sets of equations, a pair of shear and moment equations for segment AB and another pair of equations for segment BC. Step 3. Cut the beam in each segment and draw the free body diagram of the left part of the beam. Step 4. Write the equilibrium equations for each free body diagram and solve them for the unknowns. For the first free body diagram we have sum of the forces in the y direction equals 375 minus 100x minus v equals 0. Sum of the moments about the cut point equals 375 times x minus 100 times x over 2 minus m equals 0. Solve the first equation for v and the second equation for m. So v equals 375 minus 100x and m equals 375x minus 50 times x squared. Both equations are valid for x between 0 and 5. For the second free body diagram we have sum of the forces in the y direction equals 375 minus 100 times 5 minus v equals 0. Sum of the moments about the cut point equals 375x minus 100 times 5 times x minus 2.5 minus m equals 0. Solving the equations for v and m, we get v equals negative 125, m equals 1250 minus 125x. In summary, shear in the beam is represented using these equations. And moment in the beam is represented using these equations.